All right, let's work through this SI sheet. This sheet should cover the material Dr. Mullins covers on Friday. So let's start with the first side, which is predicting the products and showing the mechanism. First, we have a carboxylic acid, and we are reacting this with ethanol and sulfuric acid. This type of reaction is called the Fischer esterification. Fischer esterification. And this is a really important reaction in biochemistry because it turns a carboxylic acid into an ester. And because we're working with ethanol, and ethanol has 2 carbons, on the ester, there's going to be 2 carbons as well. So let's show the mechanism of this. So first, what occurs is this ethanol and sulfuric acid are going to react with each other. And this is going to create a protonated ethanol. Ethanol with a positive charge. And this then allows us to have a proton source in order to protonate the carboxylic acid. Because what we want to happen is we want this ethanol to attack the carbonyl. But ethanol is a poor nucleophile, so we're going to make the electrophile a stronger electrophile by protonating the carbonyl oxygen. So that's the first step. And this is going to give us the protonated carbonyl, stronger electrophile than just a normal carbonyl. And that allows a poor nucleophile, like ethanol, to attack. And let's show the result of that. Now we are going to have a ethanol with a positive charge and 2 hydroxyl groups. How do we get rid of the positive charge? Deprotonate using another ethanol. And that is going to give us a neutral molecule. Let's zoom out a little bit. If we look at what we have right now and the product, there's a couple things we need to do. First, we need to get rid of one of these hydroxyl groups. We need to form a double bond between another hydroxyl group and then also get rid of that proton. Those are the 3 things we need to do, so we're going to work on doing all 3 of them. First, we're going to start with trying to get rid of one of these hydroxyl groups, but alcohols or hydroxyl groups are poor nucleophiles, or they are poor nucleophiles, but I wanted to say that they're poor leaving groups. So in order to make it a better leaving group, we are going to protonate it. So we'll use a protonated ethanol to protonate that hydroxyl group and make it a better nucleophile. Or better leaving group. I did it again. So now the hydroxyl group is protonated. It's a better leaving group. And what are good leaving groups going to do? They're going to leave. And the result of this then is we get positive charge on that carbon. So next we can show resonance in order to create that double bond that we want in the product. So we'll show resonance. And still have our ester group on here. So now the positive charge is on the carbonyl oxygen. So what's separating us from where we are in the product is we just need to deprotonate that carbonyl oxygen. So we'll take ethanol and deprotonate it. And that gets us to the product. All right, next reaction. We are using lithium aluminum hydride, a reductant. So it's going to reduce the carboxylic acid and reduce it down specifically to a alcohol group. And instead of there being a carbonyl, there are now going to be two hydrogens on that instead. So let's first draw lithium aluminum hydride. What that's going to look like. Aluminum with 4 hydrogens, and aluminum has a negative charge. And if you care about the lithium is just going to be hanging around with a positive charge. If we would draw on the dipoles would be going towards the hydrogens because hydrogen is more electronegative than aluminum. And given that, in this molecule, the hydrogens are the ones that are owning these bonds, meaning that the hydrogens are going to be the ones that act as nucleophiles. So that's what's going to happen. Hydrogen is going to act as a nucleophile, but instead of hydrogen attacking the carbonyl right away, it's first going to actually take this hydrogen on the carboxylic acid. And the reason for that is that this hydrogen on the carboxylic acid is pretty acidic, has a pKa between 4 and 5. So a hydrogen is going to deprotonate the hydrogen on the carboxylic acid first to make H2 gas. I won't show H2 gas because in this class, we're not too worried about the byproducts. We're just worried about the major products. So the result, first step is we're going to take off that hydrogen and leave oxygen with a negative charge. And really what's going to happen is lithium is going to come over here then and hang out with this oxygen and act as a countercation. All right, so now what we're going to do next is we're going to use the rest of the molecule of the lithium aluminum hydride in the next step. So in this first step, we took off 1 hydrogen off the aluminum. So now aluminum is going to have 3 hydrogens left over. So what happens next then is this oxygen is going to attack aluminum. And it can do that because aluminum just lost a bond in the previous step. So it is able to gain 1 more bond. And then at the same time, this hydrogen is then going to come in and attack the carbonyl to put on 1 hydrogen onto that carbon. So the result of this then is we lose that double bond. And instead, there's now a hydrogen in there, which I'm not going to show, but just so you are aware. That oxygen still has a negative charge. Lithium's still going to hang out with it. And now this oxygen is going to be attached to an aluminum with 2 hydrogens. So we don't want this group here anymore. So we want it to leave. But in order for it to leave, it's going to need to be kicked out. So we are going to use the electrons on this oxygen to form a double bond. And then this is going to cause this oxygen group to be kicked out. And if we draw the result of this, we then have, we reformed the carbonyl and we kicked out that oxygen connected to aluminum. So right now on this carbonyl carbon, we have 1 hydrogen, but in the products, we want 2 hydrogens there. So now we're going to take another version of lithium aluminum hydride, and we are going to now add on the second hydrogen, and pushing the electrons onto the oxygen. So now we end up with this, and we put both hydrogens onto that carbon. Now what's separating us from where we are in the product is we just need to do the acid quench in order to create this oxygen into an alcohol. So that's that reaction. Next one, chromic acid. Chromic acid is going to oxidize alcohols. Because it's a primary alcohol, we're going to oxidize it to a carboxylic acid. So chromic acid, let's draw it out. It's going to look like this. And what's going to happen first is we are going to have our alcohol group attack chromic acid, and then we're going to have one of these hydroxyl groups leave. And let's draw the result of this. Now this alcohol is going to be attached to the chromic acid, and the alcohol is going to have a positive charge. So let's deprotonate this alcohol to get rid of the positive charge. We can use the hydroxyl group we just kicked out, since it has a negative charge, to deprotonate that. And I think I'm missing, yeah, I'm missing a whole bunch of carbons. So that should look like that, and this should look like this. All right. So now we want to form a double bond on this oxygen. So we can take a hydrogen here, because if we star this carbonyl carbon, you'll see that it has 0 hydrogens, but right now where we are, it has 2 hydrogens. So we're going to have to get rid of both of them. So first, we can deprotonate that hydrogen, form a double bond onto the oxygen, and then kick off the chromic acid. So now we get an aldehyde. And now let's turn it into a carboxylic acid. So we're going to want a water to attack, but we're in acidic conditions. So if we would have water attack right away, that would create a negative charge onto this oxygen. We're in acidic conditions, so we don't want that to happen. And also water is not a very good nucleophile. So let's first make this a better electrophile. So we'll just take H3O plus. And protonate it. And now we have a better electrophile, which allows water to come in and attack. So now We have water on here with a positive charge. So we want to get rid of that positive charge, so we can just take another water. And have that be deprotonated. I'm starting to run out of space, so I'm gonna go down.